So let's talk about even and odd functions, and we'll take a look at some examples. First, let's look at the definition for even and odd. So even and odd is kind of a little test. It says if we plug in negative x and we get our original function back, we say that's an even function. We can look at some things graphically, which we will do. Even functions are going to have y-axis symmetry, and therefore if you have a positive xy point, first quadrant point, you will get an identical second quadrant point, and that's the same thing as saying y-axis symmetry. Let's take a look at odd functions. Odds are kind of the exact opposite. It says if we plug in negative x into my function and I get the exact opposite function back, that's an odd function. Odd functions have origin symmetry, and this is more of a first quadrant, third quadrant type of symmetry. So that's the points we're looking for. So let's look at some examples to really highlight this. So the test says plug in negative x and see what happens. So if I take negative x and square it, I will get x squared minus 5, which indeed is my original function. So an even function says if you plug in negative x, you get your exact function back. That is an even function. So let's take a look at pictures of this. And so we see below, here's the picture of x squared minus 5. And I'll take a look at this on Desmos, and we can see that there are some points here. I'll pick 2 points there. So that's 2.236 and negative 2.236. It's got y-axis symmetry. I could look at other points if I wanted to. 2 comma negative 1, and I should have negative 2 comma negative 1 on the other side. So that's the y-axis symmetry. Let's take a look at our next example. So if we plug in negative x into the g function, when I cube a negative, I'm going to get negative x cubed minus 1. And so what we're looking for is either the exact same function back or the exact opposite. And this is obviously not the exact same function, and it isn't the exact opposite. The exact opposite would be this. Now it's not the exact opposite. So this is a neither function. If we look at the graph, one of the things we can look for is the idea that we saw in the notes here is a first quadrant and then a third quadrant matching point. So if we take a look at that as a picture, let's take a look. Make sure I can pull this up here. Let's turn that equation on. There we go. And let's zoom in on this. Let's zoom in. Let's take a look. X cubed minus 1. And actually, I don't have the right equation there. There's my x cubed minus 1. Now let's take a look. Now the question is, do we have a first quadrant point that matches, say, a second quadrant point? So we've got this point here, 1.236. Can we get that to match? We go all the way up to 2 and make this an integer value. Let's go up here. Let's try to get to 2 for y. So 1.44 and 2. Do we get that same thing when we get to the third quadrant? No, to get to negative 2, in fact, I got to go way, way down here. And so that's not going to work, right? So we don't have this first quadrant, third quadrant symmetry, and therefore this equation is not odd. It's neither. Let's take a look at our third example. 5x cubed minus x. So we go h of negative x, okay, negative, and negative. So this is going to turn into negative 5x cubed plus x. And indeed, that is the exact opposite of what we started with, the exact opposite. So this is an odd function. We can look at the picture there. Let's look at it on Desmos. And let's see if I can turn the correct equation on this time. And here we go. All right, so let's zoom in on this a little bit. And maybe one of the points that I'll take is not first quadrant, third quadrant. Maybe I'll do second quadrant, fourth quadrant. So the symmetry is the same idea, either first to third or second to fourth. So there's an example of an odd function that has what we call origin symmetry. And let's take a look at our final example, which is the absolute value. So if I were to do f of negative x, that would be the absolute value of negative x, which is the absolute value of x. It's the same thing, so we're getting the exact same function back. So this one is even, and if we look at that on the calculator, again, we're looking for y-axis symmetry. We're looking for 0.2, comma 0.2, negative 0.2, comma 0.2, and we can look at those types of symmetries wherever we select. So that is an even function. And those are the pictures there. So let's just look at some random pictures and let's see if they're even, odd, or neither. So you can look for symmetry. You can look for matching points, 2, 0, negative 2, 0, so that's even. Here we're going to look for a first quadrant point and then a third quadrant point. So do we have, 1/2, 1 point something? Do we have that in the third quadrant? No, that point doesn't exist. Do we have anything here and then over here? Do we have those points? No, they don't match. So this is neither. And then finally odd. So first quadrant, third quadrant, matching. Fourth quadrant, second quadrant, matching. So that would be odd. Let's talk about what functions are doing, increasing, decreasing, or constant. So in this particular, we could say we are increasing. X is in the interval from 0 to 2. So notice that we always do behavior in terms of x values. I didn't ask you how high it went. It has nothing to do with 4. I don't care about that. I care about x values in terms of increasing and decreasing or constant. So for constant, x would be on the interval from 2 to 5. Let's take a look at another maybe more complex picture. So let's see if we can find increasing, decreasing, and constant. So let's start with the increasing first. So increasing, x is going to increase from negative 4, and it's going to increase all the way until I get to 0. So let's take a look at that. So from negative 4 all the way to 0 is an increment of increasing. And that's it, right? This is going to be a constant, this is going to be a decrease, and this is going to be a decrease. So my only increasing increment is going to be negative 4 to 0. So what about decreasing? Now x is going to decrease in two different places. From negative 6 to negative 4, it's going to decrease. And that was our first one right here. From here to here, we're decreasing. And then we're also going to decrease here on the tail end. So that's going to be from 3 to 6. And then there's a constant. X is constant. The function is constant from 0 to 3. So there's the increasing, decreasing constant. Now something that should be pretty obvious is that if you think about like being on a roller coaster, you go up the roller coaster, you get to the top, you usually pause for effect to scare you a little bit, and then you come back down. So when you change from increasing to decreasing, what you are is creating a maximum, and vice versa. If you were decreasing and then you start increasing, you've created some minimum. Here we have the book definition that we don't need to worry too much about. We can see these simply from pictures, and we can talk more about algebraic increasing and decreasing as we go along. So even though this isn't a perfect graph, we're going to say that this is right on the integer values. Let's say that's on 3, let's say that's on 1, and we'll say that's on negative 1. Just to make things nice, I try to make the best picture that I could. So what are the local maxima in this picture? Well, it looks like there's only one of them. And so we have a maximum at 1, and that maximum is y equals 2. So location at 1, how high is it? It's 2. Same thing with the local minimum. So at -1 or 3, right? So at -1, location, and at 3, and that makes minimums of y equals 1 or 0. So then we could do increasing and decreasing, because if we have maxes and mins, we must be increasing and decreasing. So when are we increasing? X will be increasing from -1 to +1, and then it'll go from 3 all the way to infinity. And then we're decreasing. X is going to decrease from -infinity all the way to -1, and then from 1 to 3 it also decreases. So let's take a look at one using technology, and let's see if we can find the maxima and minima. So I'll do this both on GraphCalc, and we'll do it also on Desmos. So on GraphCalc, what you want to do is you want to zoom in pretty closely to the max or min. We go to trace, snap to max min, boom, there it is. So 0.82 and -1.53, and then I go back and hit that again. I'll zoom back out, come back up. Let's zoom in on the maximum here, just as we did before. Snap to max min, there it is. -0.82 and 11.53. So back to our notes, and so we say we have a min of -1.53 at 0.82, and we have a max of 11.53 at -0.82. And then where are increasing and decreasing? So we're increasing, so -infinity to -0.82, and then from 0.82 on to infinity, and then we're decreasing from -0.82 to 0.82. That'll create our maxes and mins. And our last topic is average rate of change, which is just a fancy way of saying slope. See this formula in a textbook, f of b minus f of a over b minus a, and I'm going to show you how simple it is because you all know how to do slope. So let's find the average rate of change from 1 to 3, 1 to 5, and 1 to 7 for this equation, f of x equals 3x squared. All right, so let's do f of 3. That's going to be 27. And let's do f of 1. That's going to be 3. So what I want to show you is that these are y values. We'll call that y sub 1, and we'll call that y sub 2, say. So slope is simply the change in y over the change in x. So that's just simply 24 over 2, which is 12. Let's do the next one. So f of 5 is going to be 75, and f of 1 is still going to be 3. So the rate of change is the y values, 75 minus 3, over the x values, 5 minus 1. So that's 72 over 4, and that's 18. And then from 1 to 7, so let's go f of 7, that's going to be 49 times 3, that's going to be 147. F of 1 we know is still 3, so that's going to be 144 divided by 6, which is 24. That's it. So the average rate of change is nothing but slope, and I have those lines on the slide here as a picture, and if you look really closely, you should be able to see that we're going from these ordered pairs up to these ordered pairs right here.
John Morrison, and Rami Youssef. Please come to the headmaster's office immediately.
And finally, the secant line. The secant line is nothing but the slope turned into an equation. So take the average rate of change that you found, which is slope, make an equation, and we call that the secant line. So let's just do one real quick. So from -2 to 1, so f of -2, that is going to be 3, -2, -2, -2, plus 3. And so that's going to give us 4, 12, 16, and 19. And then f of 1 is just going to be 3 minus 2 plus 3, which is going to be 4. So the slope, or the average rate of change, is going to be 19 minus 4 over -2 minus 1. 15 over -3 is -5. And now all we need to do is create an equation with that slope. So what we've done is we've created ordered pairs. We've got -2, 19, inputs and outputs, and we've got 1, 4, and we've got a slope of -5. So you could do this in a variety of ways. You could do y equals mx plus b, and you could say 4 equals -5 times 1 plus some unknown b. So then b is 9. Therefore, y equals -5x plus 9. And that would certainly be sufficient. To me, that's one of the easiest ways to do it. You could do point slope also. Do y minus 4 equals -5x minus 1. And then you could just manipulate that, and of course you'd get the same thing, -5x plus 9. So that's the equation of the secant line.